learners, welcome to the next session. In this session, we are going to discuss about quantum Euclidean system calculation. So the lecture outline is quantum Euclidean system calculation, Euclidean space in quantum mechanics, quantum circuits for Euclidean distance, role of Euclidean in quantum algorithms. Euclidean space in quantum mechanics. A quantum Euclidean system calculation typically involves using quantum computing techniques to compute the Euclidean distance between two vectors or points in high-dimensional space. This is particularly useful in quantum machine learning, optimization, and cluster calculation and doing the cluster task. As per the definition, equivalent distance between the 2 points A, which is equal to A1, A2, up to AN, and B, which is equal to B1, B2, up to Bn in n-dimensional space, which is given by d of A, B, which is equal to root of sigma n I to 1 Bi minus Ai of square. This formula measures the straight line distance between the 2 points in equivalent distance. In quantum computing, this calculation can be accelerated using quantum parallelism and amplitude encoding. Quantum representation of vectors. To compute the equivalent distance on the quantum computer, amplitude encoding is to be very important. Amplitude encoding in the sense the vector A and B are encoded as a quantum state as we represented as ket A equals 1 over norm A times the sum from I equals 1 to n of a sub I ket I, and also ket B equals 1 over norm B times the sum from I equals 1 to n of B sub I ket I. So this encoding ensures that the components of vector are represented as amplitudes of quantum states. And in the case of normalization, the norm of each vector A and B is calculated to ensure the proper encoding is to be introduced in the quantum circuit for equivalent distance. The quantum calculation of equivalent distance typically involves the following steps: state preparation and swap test. In this state preparation, prepare two quantum registers to represent the normalized state ket A and ket B. Use techniques like amplitude embedding or analog encoding to load the vector data into these quantum registers. The next is swap test. The swap test is commonly used to compute the overlap between two quantum states. So here we are going to introduce qubits as the ket 0, and we are going to apply the Hadamard gate and controlled swap gates between the registers holding ket A and ket B, and apply another Hadamard gate to the qubits. Measure the ancillary qubits also. So the probability of measuring ket 0 in the ancillary qubits gives the information about the inner product of modulo squared of the inner product A and B. Next, we are in the computing distance. Using the relationship between inner product and equivalent distance, we can directly go with that d of A and B squared equals norm A squared plus norm B squared minus 2 times the absolute value of the inner product of A and B. So this is about the relationship between the inner product of norms A and B. So the inner product of modulo squared of the inner product A and B is obtained with the help of swap test. So the role of equivalent distance in quantum algorithm, quantum k-means and clustering. Classical context, equivalent distance is used to determine the similarity between data points and the cluster centroid in classical k-means algorithm. In quantum extension, quantum version of k-means aims to leverage quantum parallelism to speed up the distance calculation. However, direct quantum computation of equivalent distance is challenging due to the need of the classical post preprocessing. So that is a very good disadvantages in classical thing, and we can easily overcome this in the quantum computing. So quantum support vector machine kernel method also to be introduced. Equivalent distance is often embedded in kernel function used by SVMs. Quantum algorithm like QSVM can leverage the quantum parallelism to speed up the kernel evaluation, indirectly benefiting from the equivalent distance calculation. So quantum approximation optimization algorithms are also there. Optimization problems while not directly computing equivalent distance, QAOA can be applied to optimizing problems where distance metrics are crucial, such as in graph problems or matching learning tasks. Challenges and opportunities here is quantum distance metrics. Directly computing equivalent distance in quantum context is complex due to the need of classical post-processing and measurement collapse. However, quantum-inspired methods like Schrödinger equation for approximate distance calculation offer innovative approaches. Quantum classical hybrids. Many quantum algorithms rely on hybrid approaches where classical methods are used for distance calculation while quantum computing accelerates other parts of the algorithm. In future direction, quantum machine learning algorithm also to be used. Quantum inspired methods are also to be used with the help of Schrödinger equation for fast distance computation. Limitation of equivalent distance in quantum computing. Here we can go with the integrated classical data analysis in quantum computing. So we may have some of the challenges is there. Crush of dimensionality. Equivalent distance becomes less effective in high dimensional space as distance between points tend to become similar, reducing its power. Sensitivity to scaling. Equivalent distance is sensitive to the scale of the data, requiring normalization to ensure accelerate the comparison. Quantum computing, in the terms of quantum computing context, quantum classical interoperability is very important, and dimensionality reduction also to be treated as very important consideration, and algorithm design also. Addressing this simulation, we can go with a hybrid approach of quantum computing with other classical methods, and alternative distance methods also to be there, with the help of to overcome all kind of this equivalent distance methods. Thank you, learners. We will see in the next session.